All right, we are on the 2026 edition of the AP Physics 1 exam for your response, and we are looking at question 3 now. So I may be able to stitch these videos together on YouTube, and if I can, I'll just do that instead of doing two separate videos, but we'll see what turns out here. Now, this one, I think I want to say this was the easiest question on the exam. Now, some of you may not agree with me, but I'll explain why I think that. So we got a conservation of energy thing going on here. You got gravitational potential energy to work, or energy dissipated as dissipated by friction, I think is how they like to describe that with College Board AP Physics. But anyways, gravitational potential energy equals work done by friction. And it seems that maybe a place to go wrong here is forgetting that, okay, friction is coefficient times normal force. We're on a horizontal surface down here at the bottom. So the normal force equals gravity. So long story short there, for force of kinetic friction, you can do kinetic friction coefficient times mg, replace that in here. Then we've got mu k mgd equals mgh. Hey, look, m and g both cancel out. So you get this expression h equals mu k d. So literally, if you just go through and you graph height on the vertical and distance on the horizontal, the slope's going to be mu k. Now, yeah, and if it helps, you know, hey, y equals mx plus b, and you start looking at these guys, and that's what we're doing here. It's d's going on the x-axis, h is going, and mu k is going to be the slope. Now, I think what you needed to say here is that you're going to measure height, and when they said they only want you to vary a single quantity, so the single quantity that you are going to vary is going to be that height. So you're going to measure height of release above the flat area and the distance traveled along the rough surface for many different heights, and then repeat each height several times, and somewhere, but probably just saying many different heights, and then repeat it. Repeat actually isn't necessary if you said many different heights, but I'd went ahead and said both just to make sure, like, hey, why not? Doesn't cost me a whole lot to get that. You really don't have to do a whole awful lot to get the points available there. Yeah, so let's flip over. Now they gave us this other experiment. I started doing all this crazy stuff here, and then I looked down here. It's like, oh, they just gave me the equation, and boy, howdy, did they make this easy for you folks. So they set this up, so if you just saw y equals mx, what could I possibly do here? Okay, d is going to go on x, v squared is going to go on y, and then the slope will be equal to this thing. Don't try to go and do a whole bunch of solving to get something by itself. Just do that. So all you got to do, figure out some v squareds, and you are going to graph what you figured out for your v squared, and don't forget to tell the unit is meters per second and squared, or you could have said meters squared over second squared. I don't know, maybe there's another way to do that, but wow, that would have been rough to try and, I mean, I guess you could have factored the 2g out. That wouldn't have been a whole lot of work, and then you'd have had less stuff to do, but it's not worth it. Part D, at least tell them the slope equals the thing, like, so the 2g sine theta minus mu k cosine of theta. That's worth a point. And then the other point is for finally figuring out it's 0.55. So basically what I did here is I didn't even try to do any symbol algebra kind of stuff. I just started plugging in numbers immediately. Sine of theta is 0.5, cosine of 30 is 0.866 something. And you just algebra your way through this and eventually end up with 0.55. I hope I did my math right here. I'm sure somebody will troll me in the comments if I didn't. That seems like an awfully high coefficient of friction, at least for common lab surfaces, but I mean, I guess it could be like some sandpapery or concrete or something. I don't know. So if I messed up there, feel free to roast me in the comments, but this is the general idea. They do give you, I don't know, 10% or something, some reasonable range of values here. So if you actually didn't graph it in Desmos or something, that's fine. Like, you could have actually found picked a couple of points on your best fit line and found the slope between those 2 points or something, that would have been fine. Now, this problem, number 4, this thing gave me all kinds of troubles, and it really wasn't that bad. One thing that really did help me as I was going through this is just realizing, hey, the one with less rotational inertia is going to be the one that's easier to spin. So that is going to help you with the reasoning here. So somehow or another, they said justify your answer using qualitative reasoning that goes beyond equations, beyond referencing equations. So basically, you just had to say here that the toy Y has the smaller rotational inertia. So that means if it receives the same torque for the same amount of time, I even went in and said, hey, that's the same angular impulse, it'll have a greater rotational angular velocity because it'll have the same amount of angular momentum, but the one with the smaller rotational inertia must spin faster. I probably said too much here, but yeah, somewhere in there, I think I got all the, or would have gotten all the points that they desired. I hope that I don't have to score this one because holy cow, those two approaches they said here about work energy theorem or Newton's second law in rotational form, I was like, ooh, Newton's second law in rotational form, I know that. Torque, alpha equals sigma torque, sigma tau over moment of inertia or rotational inertia. And that ended up being a way that I would never recommend somebody to do this based on the terms that they gave you to report your answer in. After doing it, I would highly recommend taking the work energy approach to that. And maybe I could have found a simpler way to do this than I did, but in the moment, as I was working through it here after school, trying to get done so I can go home on a Friday, maybe I missed a easy thing here. Like maybe I could have done something differently here to make this easier. But the pathway I took on this thing was terrible. I don't know. I don't know if it's worth me trying to explain what I did here, but I guess it's sure. Let's see. So anyways, yeah, it started with Newton's second law in rotational form. And the first thing I did, and this might have been where I made a mistake, maybe if I had done A divided by R or something here, maybe it would have went better instead of doing but I had to get that. I had to get omega in there somehow. So maybe it could have been easier. I don't know. Long story short, stuck this in place of alpha, the delta omega over delta t angular velocity thing there. Then I cross multiplied those, and then I solved for delta omega, and then I realized that the initial angular speed, angular velocity here was 0. And then I got over here and I was like, okay, torque, that's fine. I can do the FO times RO thing for torque. You're just like, hey, look, that times that gets you torque. But then, yeah, and you can see I kind of stopped telling where things were coming from. Just like, hey, we're doing this. And then I was like, oh, snap, I got to deal with the time. And so I just thought about that for a minute. I actually came over here on a sticky note and did some sticky note math to get to the point of realize, okay, this is the way I can deal with that. So starting with the second kinematics equation on the reference sheet, realizing that I'm starting from a position of 0 and an initial velocity of 0, and this is linear math. Like I was doing linear math because I'm pulling on a linear string and it's going to accelerate in a linear fashion. And yeah, I get that. I'm like, okay, that's equal to time squared. And I'm like, hey, let's use, this thing for acceleration in a linear fashion equals the radius times angular acceleration. Replaced angular acceleration with delta omega, which we talked about over here. Delta omega was just omega f because omega I was 0 divided by time. Again, the initial time was 0. Maybe I didn't say this already, but the initial time was 0. So the final time, the interesting time would be t, but that's going to cancel out anyway, so it's not a big deal. So long story short, blah, 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 all this stuff. I plugged in our omega f over t in place of a, and then simplified the expression, got something to plug in for t here, which was 2xf over r omega. Now, what is xf? It is eventually LO. That's the length of the string, is how far did you pull the string. And then check this out. When I plug that in, put the stuff in here, the RO's canceled out. And what else did I have to clean up? Yeah, I replaced, or yeah, omega f down here, multiplied that over to the other side, then had omega f squared equals all this stuff. And finally I square rooted it and replaced xf with hello, and yeah, made sure I had it all in terms of things. And then I said, wow, that was a lot. So I thought to myself, you know what, I bet it's easier the other way, because by that point I'd realized, you know, if we did work energy theorem, hey, work is FD, and we're doing rotational kinetic energy here, which is 1/2 I omega squared. And sure enough, you plug in the distance you're pulling on is the length of the string, and then FO is the force you're applying. And 1/2 I omega squared, you know, moment of rotational inertia of the toy, and omega f of the toy, which they called omega x, but whatever. We're looking for this expression. That's the one that they care about. So long story short, you get to the same place. Like I wasn't even sure that was right when I got done, because I'd done so much and that was so hard, and I was just like, why did I do this to myself? So anyways, long story short, I got the same answer doing work energy. I found work energy to be much, much easier. And then it said justify how your derived equation is consistent or not consistent. I said it is consistent because Ix is in the denominator, so if its value were decreased, then the rotational inertia would be, or excuse me, not rotational inertia, the angular velocity would be greater. I guess we can see that clearly here. If you make that one smaller, divide by a smaller number, you get a larger number for omega f. So there you go. That's the AP Physics exam for 2026, and hopefully I got most of it right. So we'll see when we get to the reading. I definitely don't want to score part B of the question 4. Wouldn't mind scoring the lab question. I'll probably score the lab question because I've done that one many times, or most of the I think I've scored the lab question like just the last 2 or 3 years I've scored the lab question. This thing, I don't think this will be too bad. I'm not sure about this whole thing about the fact that the speed, like if you read it wrong, you still get the right answer. I'm not sure how that's going to go. And then this thing, that's probably not going to be fun to score. So I'm going to go with hoping I don't get question 1 or question 4 for the reading this year. Y'all have a great summer, and take care.